Welcome to today's lecture. This is still a series on radioactivity, part 11. Today we'll be looking at numerical questions on mass energy interconversion. Remember, in part 10 we looked at Albert Einstein's theory of relativity, where we stated that mass and energy are interconvertible. That is, mass can be converted into energy and energy can be converted into mass. Today we're going to look at numerical questions on mass energy interconversion. So let's get started. Question number 1. Calculate the energy released when a mass of 2 grams is converted completely into energy. We are given C with the speed of light or speed of electromagnetic radiation, 3 times 10⁸ meters per second. Don't forget that formula we committed to memory in part 10, Albert Einstein's theory of relativity. E is mc squared. So, but our mass is given in gram. We need to convert the mass to kilogram. Of course, you have to divide a gram by 1000 to take it to kilogram. If you do that, 2 divided by 1000, that will give you 2 times 10⁻³ kilogram. And then we quote the formula E is mc squared. M is 2 times 10⁻³. C is given as 3 times 10⁸, of course, squared. If we resolve this, we're going to get 9 times 10⁻16. And resolving everything here gives us 1.8 times 10⁻14 joules. Question number 2. What mass is equivalent to an energy of 9 times 10⁻16 joules? Again, E is mc squared. We are given C to be 3 times 10⁸ meters per second. We're told what mass. So here we're looking for mass. We make M subject of the formula. That's E over C squared. We know what E is, 9 times 10⁻16 joules. C squared, we're writing it twice because it's squared. And by the time we resolve that, we'll get 9 times 10⁻16. 3 times 3, 9. 10⁸ times 10⁸ will give us 10⁻16. In indices, when the base are the same, and the operational sign is multiplication, you add the power. So 8 plus 8, 16. By the time you resolve this, you're going to get 1 kilogram. Question 3. A nucleus has a mass defect of 3.0 times 10⁻29 kilogram. Calculate the binding energy of the nucleus. We are given C to be 3.0 times 10⁸ meters per second. So we're told the mass defect is 3.0 times 10⁻29 kilogram. We are given C. If you put everything there now and you resolve accordingly, this will give us 9 times 10⁻16. And if we resolve accordingly, 3 times 10⁻29 times 9 times 10⁻16. If you resolve this accordingly, you will get 2.7 times 10⁻12 joules. Question number 4. The mass defect of a nucleus is 0.015 atomic mass unit. Calculate the binding energy in mega electron volt. We know that 1 unified atomic mass is 931 mega electron volt. we're given the binding energy as 0.015 unified atomic mass. This is the binding energy, so we just convert it to mega electron volt. Of course, 1 U is 931 mega electron volt. So we multiply 0.015 by 931 mega electron volt to give us the binding energy in mega electron volt. So once we do that, you're going to get 13.97 mega electron volt. We go on to question number 5. How much mass is converted to energy when 1.8 times 10 raised to the power 14 joules is released in a nuclear reactor? Of course, we're given C again. So E is mc squared. How much mass? So we're looking for mass. We make M subject of the formula. So M is E over C squared. The energy is 1.8 times 10 raised to the power 14, and C is 9 times 10 raised to the power 16. The square of this. By the time you resolve properly, this will give you 2.0 times 10 raised to the power minus 3 kilogram. This will take us to question number 6. A nucleus of mass 4.030 U, that is unified atomic mass, disintegrates into another nucleus of mass 4.002 unified atomic mass. Calculate the energy released in the process. We're given 1 U to be 931 mega electron volt. 1 electron volt is 1.6 times 10 raised to the power minus 19 joules. So don't forget our mass defect is M1 minus M2. I explained this in our previous video or lecture. So our M1, we're taking M1 minus M2 because during disintegration, the initial mass is always greater than the final mass. So our initial mass is 4.030 unified atomic mass minus 4.002 unified atomic mass. That will give us 0.028 unified atomic mass. This is already what we call binding energy. So we just convert it to mega electron volt and then finally to joules. So we just multiply that value by 931 to take it to mega electron volt. So if we do that, that will be 26.1. Mega means 10 raised to the power 6. Electron volt 1.6 times 10 raised to the power minus 19 joule. I would like you to resolve and put your answer. Number 7. A radioactive nucleus of mass 238.050 unified atomic mass decays into a nucleus of mass 234.043 unified atomic mass by emitting an alpha particle of mass 4.003 unified atomic mass. Calculate the energy released. We're told 1 unified atomic mass is 931 mega electron volt. You should be familiar with this by now. The total mass before decay, before disintegration, is 238.050 unified atomic mass is given in the question. After disintegration, after decay, we have a mass of 234.043 and an alpha particle of 4.003 unified atomic mass. So we need to add up to get the mass after decay. So when you add up, you're going to get 238.046 unified atomic mass. Don't forget our mass defect is delta M, which is M1 minus M2. Our M1 is the mass before decay, before disintegration. That's 238.050 unified atomic mass minus the mass after disintegration, the total mass after disintegration, 238.046. And by the time we finish up this, we get 0.004 unified atomic mass. So this is our binding energy. So the energy release will just be by You will get the energy released by multiplying this value by 931 mega electron volt. Once you do that, you will arrive at 3.72 mega electron volt. Number 8, which is the last question we're considering. A nucleus loses a mass of 0.002 unified atomic mass during a nuclear reaction. Calculate the energy released in joules. We're given C. We're told in this case 1U is 1.66 times 10 to the power minus 27 kilogram. Of course, we need to convert 0.002 U to kilogram by multiplying by 1.66 times 10 to the power minus 27 kilogram, because we're not given 1U as 931 mega electron volt. So when we do that, we're going to get 3.32 times 10 to the power minus 13 kilogram. So quoting the Einstein's equation, our mass is 3.32 times 10 to the power minus 30 kilogram times the value of C squared. And when we resolve carefully, don't forget this will give you 9 times 10 to the power 16. We've been doing that for quite some time now. So if you resolve this carefully, you will get 2.99 times 10 to the power minus 13 joules. You would attempt the following questions for me. You will take your time to go through all the videos starting from part 1 up to part 11, just to help you gather a proper understanding. And then with all that you have now, you should be able to solve the questions given below. Question 1. During a nuclear reaction, 0.25% of the original mass of 2 kilogram is converted into energy. Let's take it again. During a nuclear reaction, 0.25% of the original mass of 2.0 kilogram is converted into energy. Calculate the energy released. Of course, we're told C is 3 times 10 to the power 8 meter per second. Number 2, given that one proton is 1.0078 unified atomic mass, one neutron is 1.0087 unified atomic mass, calculate the binding energy of helium. Helium is 42He. Try to attempt this question. Go through the solved or worked examples properly, get a proper understanding, and attempt these questions.